The nature of this experiment is to demonstrate Newton's first law of motion, also known as law of inertia. The experiment will need narrow mouth bottle, embroidery hoop, and a stack of bolt nuts or coins. This is to show that objects don't move unless a force acts on them, and if a force is applied quickly to the surface beneath them, they can remain in place due to their inertia. To win this, the movement should be sharp enough to remove the hoop without disturbing the nuts resting on top, so they would go down straight to the bottle. The technique is successful because of inertia, which is the tendency of an object to resist changes in its motion. The nature of this experiment is to show that you can move or pull a heavy object using only small force by using the right setup. This experiment will need a couch and an angled rope. Sideway force can result to a large pull because when you pull the ropes at an angle, the tension spreads out on both sides. As the angle gets smaller, those tension forces become stronger. This technique could also be used in towing or moving vehicle, pulling boats to the shore, tightening tents, rock climbing, and using come along or ratchet strap to move or lift objects. It is possible because when you pull the rope at an angle, the tension in the rope creates a much larger force on the object you're pulling, so even a small effort from you can produce a strong pulling force on the object. The nature of this experiment is to demonstrate Newton's third law of motion, showing that for every action, there is an equal and opposite reaction. This experiment will need a balloon, wire or guide string, and paper clips. The inflated balloon moves when the air escapes because according to the Newton's third law of motion, for every action there is an equal and opposite reaction. The air pushing back creates an equal and opposite reaction on the balloon. There would still be rocket action even if there is no surrounding air because the action of the balloon moving is not dependent on the air pushing back on the surrounding air, but on the sudden expulsion or rush of air out of the balloon, which produces an equal and opposite reaction on the balloon. The nature of this experiment shows an object in motion stays in motion unless acted upon an external force. When the moving cart suddenly stops, the doll with seatbelt will stay in motion while the doll without a seatbelt is restrained. The materials needed are string, cart with a small doll, a mass, and a block. What stopped the motion of the doll without a seat belt when the cart crashed to a stop? When the doll doesn't have a seat belt, the doll kept going forward until the cart is hit the wooden block base. Based on Newton's first law, inertia, the impact made a force that stopped the motion, since no one to support the doll and the doll will throw up. Was there any difference for the doll with a seatbelt? Yes, there is significantly difference between with seatbelt and without. The seatbelt was a help to prevent the doll to being thrown forward during the sudden stop. If we set up a track in this orientation and let a toy car slide from a specific height of point A, it will then travel to another height point B. The gravitational potential energies at point A and B should be the same, as they have the same height, given that the track is symmetrical. Then by the law of conservation of mechanical energy, the potential energies at point A and B should be the same, as these are the points where the kinetic energy is zero. Intuitively, if we let go of the toy car from point A, it should end up at point B. The efficiency is defined as how much usable energy was produced or output relative to how much energy was needed or input, that energy in this case being the gravitational potential energy. The efficiency of a system such as these should be dependent only on the heights of points A and B, and by extension should be 1 or 100%. The nature of this experiment demonstrates how potential energy is converted into kinetic energy as the car moves down the track and then back into potential energy when it goes up the other side. That be the case in real life? Let's see. To conduct this experiment, we need a track, a toy car, and stuff like tape to secure the track in place and minimize its motion, and of course a measuring device. The efficiency of the car and track system do change if the track is not taped, because if the track is not taped, it may shift, vibrate, or have gaps and joints. Those extra motion introduce additional energy losses, so the car will not climb as high as before. There is no units in efficiency. It is dimensionless. Efficiency is a ratio of energies or height, so it has no units. It is often reported as a decimal or as a percentage. The car and track efficiency do change if the track is altered, because the efficiency is independent of the absolute height, but changing the track height changes speeds and the distance that the car travels, which can change frictional and air resistance losses.